Hi, so this is a pre-recorded class for Monday, April 5th for chemical engineering thermo. And first I was going to go through the quiz from last week and then finish up chapter 11 and then go on to chapter 14 today. So, okay, so the quiz was having to do with this paper where they are producing this 2,3-butane diol from bioreactor, like from waste, agricultural waste, and then it's in water. So it's this molecule. It's in water, so they need to separate it. So they use a solvent extraction. So they flow 2-methyl-1-pentanol into this. It makes a two-phase system, pulls the butane diol out, and then these two need to be separated by distillation. So you want to get the phase behavior of those two, the vapor-liquid equilibrium, and they use this apparatus to get the vapor-liquid equilibrium, which you can look at if you want, and then they test it with water and methanol, and they find there are measurements of the red dots and the black dots in the literature. So there's the bottom is a bubble point, the top is a dew point. So they match pretty well. And they go ahead and do measurements on their system. They do both this 2-methyl-1-pentanol, and they also look at 3-methyl-1-butanol as an extraction solvent. And then they get the phase behavior, and they've listed all the results of that here. So they have the X is the dew point, Y is the bubble point, and the two gammas that they obtained using not using the Margulis 2 parameter, but using this Uniquac model, and also using the NRTL model. So we'll talk a little bit about those. Those are in chapter 12, right? So the book talks about these, and they're using a program called Aspen, which is a standard chemical engineering calculation program, and it implements these Uniquac and NRTL and a bunch of other models. Again, there's a lot of models that you can use. I mean, the simple Margulis 2 parameter, and then you can add in a lot of different features. So the Uniquac uses group contribution. So it's going to have all the chemical species having certain numbers that contribute to the gamma, basically, the activity coefficient. And the NRTL is just a more elaborate Margulis 2 parameter that allows for clustering of the atoms. So the Margulis 2 parameter assumes that things are randomly distributed, but if there's associations, they correlate, and then anyway, these models take care of those various features. Every time they add a feature, you add a constant. You add another parameter that you need to fit. So, or look up in a table. So the Uniquac is going to have probably 15 parameters to fit the curves. That's why the fits look so good. Margulis is just a 2-parameter fit. If it's a 2-parameter Margulis or a 1-parameter fit. So you don't expect that your calculation is going to be close to what they have, but it's good to kind of see how much better it is to use a multi-parameter. Anyway, so this is using gamma fit because we have the data. So we have this data sheet paper. We're just looking at one pressure. So they varied pressure in that apparatus, got the equilibria, vapor-liquid equilibria. So we're just looking at the one X. So we have the X experimental values, the Y experimental values, which we're not going to use. We're going to calculate Y, right? So we don't use Y. And then we'll use Y to compare the calculated Y to the experimental at the end to get this plot. Delta Y versus composition. So do use Y at the end. So they have a pretty small variance in y. I guess it's 1/100% or 1% kind of change from the experimental to the calculated, right? And then, our values are worse than that. We'll end up with. So anyway, so this spreadsheet T, X, Y, fit P. So you input X, input Y, input the T experimental that he measured for the equilibria at this pressure at 0.8 bar. So they're changing the composition. They're getting this temperature, equilibrium temperature at this pressure. They raise the temperature till they see a vapor forms. Then they log all the composition of the vapor and the liquid and the temperature. They get the compositions from a mass spec, gas chromatography mass spec. So they make a vapor out of this, run it through a column. It separates according to mass, and then run it through a mass spec, and it'll separate what the vapor is into species. So they can figure out the composition, so the two components, using that chromatography. Then so basically you're gonna need to calculate the pressure right here. So this is a fit P operation. So we have yi over xi equals gamma I. So we'll talk about just one here. Gamma 1 P sat 1 over P. That's our basic equilibria equation. So if you have, and you don't know P and you don't know gamma, and you can calculate P sat from the Anton coefficients that I gave you from the list web page. So you put those in, and then you can get P sat according to what is the temperature. So temperature is an input here for this. So we can get P sat. We know X, and we need gamma 1 is going to depend on gamma 1 depends on P. So the gamma 1 calculation, see, gamma 1 depends on A12, not P, right? So gamma 1 is down here. Gamma 1's, this is the 2 Margulis gamma 1. Depends on the X, which we have as input, and we're fitting the A12s here. We want to get these two A12s, A12, A21. So gamma calculation depends on those. So you're going to vary those, gamma will change. And when the gamma changes, the P calculated is going to be, so Y1 equals, Y1 times P equals X1 gamma 1 P1 sat. Right, so we get gamma 1 depends on A12, A21, P1 sats fixed at the temperature. So everything's fixed except gamma 1. Then this thing, and the sum of those P, Y1s equals P. Oops, sorry. Yeah. So this is our parent equation, Y1. So this is the K ratio. Y1 over X1 is gamma 1 P1 sat over P. That's kind of Raoult's law. Without the gamma 1, it's Raoult's law. So it's a modified Raoult's law. And then so you can rearrange that P times Y is X times gamma P. And if you sum up the PYs, you get P. So you know P equals 0.8 bar. Right? So then we can plug in different A's to get gammas, and the gammas to get these. So A's give you gammas, these give you that, and then you get the P. So by iterating, by changing the A's, you can get the P here. And you have two unknowns, right? So you need 2 data sets, and you have 10 or so here, right? So basically you have plenty of information to get this. So this, if you do this for all of these, will give you kind of an average answer, right? So you just set up, this thing is already set up, but basically it's set up using solver. Solver routine, so that the objective is going to be the least squares. So you're going to have let's see, highlight that. The objective is here, it's L8. So that's going to be the sum of the squares of the difference in the pressure between calculated like 0.75 minus 0.8 squared, right? And then you sum up all those. You sum all those, that'll give you this 0.07. Then the solver routine will just minimize that by changing the A's. So that's already done here. So that's how this thing works, right? So you get the two A's. So that's good. And you also, once you have the A's, you can calculate the Y's because Y, so you can calculate Y from this first equation, like Y1 equals X1, which is experimental, gamma 1, which you just got, and then PI sat from Margulis, which you also have, and then P is a 0.8. So you can get the Y's. So you have the X's and the Y's, right? And then you can kind of, if you want, you could compare the Y's to the experimental Y's, but that's not the Y we're going to use for this. Right, so that's the first part of this quiz, right? Use that, report the A12s, A12, A21s, show the spreadsheet and how does it work. Then use the TXY calc tab in GAMFIT to calculate the bubble point composition and temperature. So this is where you create this phase diagram like this thing. Because before that, you're just using the experimental temperature, so you haven't actually calculated anything. You just got the A12s and the best that you could get with those A12s for the Y's. But you haven't calculated any temperatures. You haven't calculated the phase diagram. So to calculate the phase diagram, you use TXY calc T. Okay, so this guy, so you come in with your experimental X's, what you put in for the solution. Then you have the experimental Y's, but you're not going to use those except for to get the difference. And then you're going to first guess what the bubble point temperature is. So this is a bubble point calculation, and you're calculating the bubble pressure, right? And the bubble pressures should be 0.8, right? And to get the 0.8 bubble pressure, you're going to change the temperature. So you're changing, so the temperature is going to, and the A12s are fixed. So the gammas only depend on X. And so in this case, you're going to calculate PY1 equals X1, gamma 1, P sat 1. And P sat depends on the temperature, right? P sat and temperature are tied. Gamma is just at this, gamma is just calculated from X and the A12s, right? So gamma is fixed for every X. I mean, it'll be different gamma for every X, but it's fixed in this calculation because the A12s, A21s are fixed. And then X is the input, right? So these two are fixed. You're varying the saturation pressure to get this, and then you're gonna sum those. PY, the sum of those is P, and that's equal to 0.8 bar. Right, so you're gonna vary temperature, that'll vary P sat, that'll vary this P, and then you're trying to get that P to minimize to 0.8 bar. It's going to take the calculated P. All right, so they didn't take like calculated P minus 0.8 squared, because that isn't how P depends on temperature. P depends on temperature. P sat is going to be P sat's going to be an Arrhenius function, right? Exponential minus an activation energy over KT. Okay, so you have an Arrhenius function. The P sat is going to be proportional to exponential minus EA over KT. Because you have a liquid has to jump out into the vapor to get the saturated pressure, and that jumping involves the barrier energy. So there's an activation energy for that. So it's a thermally activated process, just like flow, like viscosity would also follow that law. Right, so anytime you have some kind of jumping, you're going to follow this Arrhenius function. energy, barrier energy versus KT. So some energy to jump, that's this activation energy. That means you should look at ln of P sat versus 1 over T, right? And then the slope of that is going to be negative of the activation energy. That's called an Arrhenius plot, ln of P sat versus 1 over T in Kelvin, right? That should have a negative slope. The point should follow a line. The slope should be negative E activation over K, or over R if it's in per mole, right? So the fit he's doing is a log of P and then 1 over T. So the guesses you're making are in 1 over T space, right? It has to be in Kelvin because it's basically has to be Kelvin here. And then the log of P minus log of P, which you're expecting, which is 0.8, is the same thing as, so log of P sat, log of P, the sum P minus log of P experimental equals the log of P calculated over P experimental. That's the way log works. So this difference is the ratio, right? So that's what he has here. So he's going to compare this log of P calc. He's going to sum these up. This is like a difference, and he's going to sum to this objective function. And then so it's going to be the sum of those P's here, P ratio, log of P ratio. And he's going to vary the 1 over T, because that's a linear relationship between those two. It's going to be this linear relationship. It's an Arrhenius relationship. And then, so he just guess some T, 1 over T's. He gives some hints here what to guess. And then it's going to minimize. These are the variable it's going to change, and it's going to try to get this objective to 0 or to a minimum, right? So the solver routine is to take this objective by varying these 1 over T's and then get it to go to as low as you can get it, so a minimum. So each of these is going to be really close to 0.8 because it's really doing each of these independently. So it's like doing each of these independently. It can get this to go to 0.8 exactly, almost, right? 10 to the minus 8. It's like pretty close. And then, so these aren't linked. These are just independent numbers. So it's going to generate just a T calculated that are independent of each other, right? So it'll just solve all of it all at once. So then at that point, you have the T calc, and then from that T calc, you can get the Y calc, right? From the X1, gamma 1, P1 sat divided by the total P, which you just got the total P over here. So you get your X and Y, that's the bubble point. So the gas phase, when you're forming a gas phase from a liquid, the sum of Y equals 1. That's the temperature bubble point, right? So that's the bottom the TXY plot. So those things are plotted, that Y is plotted here and the temperature is plotted there. Then he takes that same bubble point temperature. So in equilibrium with that is some X, that's the experimental X. So the top curve is the dew point. So you're making a liquid from the vapor. So the sum of X equals 1. That's your experimental X, and the temperature they just calculated for the bubble point. So you can see the match isn't great. Like it doesn't really work out very well for that. It's compared to what he got, it's a lot worse, right? Let's see. Well, you can't really see it. You can see it here. Like his match is almost perfect. This thing looks kind of not that great. But it gets a basic idea of it. It's only a 2-parameter fit. So I guess this is good enough, right? It's good enough to give a basic idea of what's going on. The Aspen code is better. I mean, you can do the same fit, this Uniquac fit using Excel from the book. Like he has that all coded into Excel. So that's part C. Then part D, I'll make a plot. That's part D, I guess. And then, oh no, let's see. Part D is to subtract the 2 Y's and then get this other plot, right? So subtract the calculated Y from the experimental, you get this plot. So it goes to about 10% error. Like the maximum is about 10% error. And he's getting like 1% error. his things, right? One or two. So it's basically his thing is much better. And you can see in these plots, it's much better. These are just a different way to look at it. And then again, like these two functions, if you looked at the wiki page, they have a lot of other parameters, like a huge number of parameters. The UniQuack with group contribution is going to have like 10, 15 parameters. And the NRTL has fewer, but basically you're adding in parameters in order to get this better fit. And I mean, how many parameters can you do? Well, each of these pairs of points, so they're paired horizontally, they're in equilibrium at given temperatures. There's like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. There's like 15 points. You could have 15 parameters. And I think they're using 10. So I mean, if they use 15 at each point, then you can just say each point is matched, right? So basically they're pretty close to using the total number of parameters that you could use with the data set, with these fits. So, but it's good for predictive. You can predict any other composition with that at that point. So predictively, it's useful. And you'll see there's some theoretical basis to these models. They're just a free-for-all Taylor series fit. All right, so that's that quiz. We get rid of that, and then we can move on here, hopefully. So if you have any questions about it, about the quiz or anything, email me. That's the parameter input. This is that paper. So, so let's see, we are on, this is where I wrote this down somewhere, 55. So there's a few things from chapter 11 I want to just go through. You've already done homework problems on these. I just want to kind of go through it in lecture to hammer home the point of some of this. So, and then we can move on to kind of the rest of the things. Let's see, this isn't exactly centered here. All right, so the first thing is heat of mixing. Right, so if you mix salt and water, it heats up. Right, if you mix ammonia and water, it heats up a lot. Right, so there's some kind of change in enthalpy that happens. This delta H excess enthalpy. So the H excess, if its ideal solution is 0, there's no heat of mixing because the two materials don't even see each other, right? But for real solutions, you can have it can cool down, like alcohol water, I think cools when you mix it. And then salt and water heats, right? And ammonia and water heats a lot, right? So basically there's this heat of mixing that comes about. And you want to know what that is because in some cases, like you take sulfuric acid and add it to water, it can blow up. So the heat of mixing is enormous. Or SO2 disulfide, right? Or not disulfide, sulfur dioxide, sorry. And you mix that with water, that's an explosion. And it's just the heat of mixing, right? So basically, the heat of mixing can be a big number in some industrial situations, and you want to know what it is. So you can measure it calorimetry. So you put it into a isolated chamber, and then just measure the heat that comes off. Right, that's one way to do it. So you put it into something called a bomb and measure it. The other way to do it is if you do this thermodynamic analysis. This heat of mixing is related to the Gibbs free energy excess, right? Through this Gibbs-Helmholtz relationship. So we had before dG/dt at T equals minus H over T squared, and these rules apply also for the excess terms, right? So this is the actual amount of heat that you make, and this is the heat per mole, right? So So the heat per mole is the intrinsic, and this is the extrinsic heat in mixing. Right. So basically, you can calculate this. You can also calculate the volume change on mixing, which is the change in this Gibbs with respect to the pressure. Right. So if you get expressions for the Gibbs excess, you can relate the Gibbs excess to the gamma, and then the gamma to the volume change on mixing, which you might want to know if you're mixing alcohol and water. There's a big volume change. Right. So then the heat is mostly for when you're mixing things like salt and sulfuric acid. So these things are important to know. So if you know the equation of state, say from your vapor liquid equilibria, you can back out a number for this. Right. And he goes through an example of getting that. This is a Margolis two-parameter model for methanol and benzene. What's the heat of mixing? And then basically it's just plugging into these equations and you get that. And there are homework problems where you do the same thing. This is nothing fancy here. It's just use that equation, use this Gibbs Helmholtz relationship, and get the heat of mixing. And then so that's pretty useful to know about, because you'll have something like Aspen will give you some kind of excess Gibbs, and then you can get the heat of mixing from that. And it'll also spit it out, but this is basically telling you like how it gets it, or how you could get it if you need to. Let's see, I'm going to skip this part. Henry's law is important. So if you're doing environmental work, right, you're dealing with like parts per million of some kind of pollutant, and then you use Henry's law. So what is it? That's kind of the key issue here. So Henry's law is used when you're in dilute conditions, right? And it turns out like we have that the Raoult's law is like the pressure equals the saturated pressure of the component times the component composition in the solution. You have a liquid and a vapor, a one component system, right? Then the pressure of the vapors, or if it's a two component binary system, then you're going to sum up these. You're going to get the pressure from the saturated pressure, right? So in other words, y equals p sat over p times x. Like that's our base equation that we're using. Right? Y over x, the k ratio is p sat over p. But if it's a Henry's law, you don't use p sat. You use some arbitrary number, right? Some Henry's law constant to get the vapor composition. Same equation. One uses p sat, one uses k. It's because when your x is so small, so x here is much less than 1, and here x is about 1. So for Raoult's law, x is close to 1. For Henry's law, x is really small. Right, so you're at the infinite dilution limit, and then the saturated pressure doesn't govern the vapor pressure of the substance anymore. It's not following this x law for this thing. So it's because the associations of the fluid become more important, right? When it's so dilute, the associations with the solvent. So this KH is going to depend on the solvent. It's going to be like a solvent solute pair, right? And it'll basically be at some temperature. Right? So it's going to be depend on the solvent solute. It's going to depend on the temperature. When you look it up in a book, you look it up on the NIST webpage. Like NIST webpage will give you the Henry's law constants for things like organic pollutants. Right. So you want to know like what's the vapor pressure formaldehyde, if it's a trace amount in wastewater. So you can calculate that with Henry's law. That's the idea of this. So that's it. I mean, he goes through a lot about Henry's law, but basically that's it. It's just when you're in pollution problem, you have a really small amount of something that's toxic, then you're using this Henry's law to calculate the pressure. Right. That's all there is to Henry's law, Raoult's law. he goes through quite a bit. Basically, we don't need to know more than that. I mean, that's all you're going to use, I think. So, like, what's the solubility of CO2 in water? I mean, that's the case where it's going to be dilute. He uses the chemistry web book to get the Henry's law constant, and they just multiply it out, and you get it. That's all there is to it, right? And usually you'd say like parts per million instead of whatever fraction he has here. This would be 4 parts per thousand, right? So that's kind of it. I mean, it's fairly simple, right? Let's see. Right, we don't need this. Then they're using a more complicated. This is just the Margulis acid-base equation, right? So it's going to be the difference between alphas and betas to get the gamma here, or to calculate the. So he's calculating gamma with the this equation, acid base, then the specific volumes. Those are the numbers from the back of the book, from the cover of the book at the end. And then you can calculate the Margulis 1,2 parameter, and then from that get the gamma, and from the gamma get the whatever the Henry's law constant from this thing. So anyway, there's problems that you did on that. The last thing, I think this is the last thing. Let's see. This is, yeah, I think this is the last thing. So it's just this osmotic pressure. And again, this is also fairly simple, right? But important. So it's because you're going to look at, there's a lot of applications like reverse osmosis. So if you want to do a separation, you can apply a pressure to a system and then drive a fluid. So you have some concentration X on one side, and you want to have it pure on the other. You run it through a membrane, a semi-permeable membrane. So semi-permeable membrane is polycellulose acetate, and it's got some kind of pores in it, right, that allow the solvent to pass through, but the solute doesn't pass through. Say you have a protein, right? You've produced a protein in some kind of fermentation process, and then you want that protein, but you don't want the water that's in, right? So you can't distill this, because if you distill it, you burn the protein, then you've ruined your product, right? It's temperature sensitive, but it's not really that pressure sensitive. So you can put the water and the protein in a reverse osmosis system, and then put enough pressure here, pump the water through, and get the protein out, concentrate the protein that way. Then once you reach a certain concentration, you can crystallize it, which we'll talk about in the next chapter. Right. So basically, reverse osmosis does this, okay, or any kind of, and you can also purify, like they talk about purifying seawater with reverse osmosis. So you put seawater on the side, the X then is the salt, and you pump it through a membrane by pressure, and you get pure water out that you can drink. Right, so there's huge reverse osmosis setups in Israel, for instance, to produce fresh water for drinking from the ocean water, right, to kind of greenify the desert or whatever. Anyway, so this is a common process. I mean, it's expensive. The membrane fouling and that kind of thing is an issue. But basically, it's pretty common now to use osmosis, reverse osmosis. So the idea is this: you have a semi-permeable membrane. Let me make it different than that. So you have a semi-permeable membrane, and you have your so you have your solvent here, and you have your stuff, right, which is going to be, say, a protein. So it's a colloid. It's a colloidal solution, or it could be a polymer, or it could be a salt. So you can have a membrane that won't allow charged species through. Right, so your ions, your salt ions like NaCl, could be stuck on one side. So whatever those things are, it doesn't matter. You just call them a thing, right? So you're going to call it a gas atom. And then you're going to forget about the solvent. Okay, so in that case, you just have a bunch of gas atoms, right? And they're each one of them moving around with kT energy. So they exert a kind of pressure, right? Which is called the osmotic pressure. So there's an analogy between a colloid suspension and an ideal gas. That's the main thing about osmotic pressure. The osmotic pressure is usually called pi, capital Pi, right? So if you use the ideal gas law, you say P, so you have like pi is RT over V, where V is the molar volume. Right? And then you can do a viral expansion of this thing. So that would be an ideal situation. And then usually this osmotic pressure, there's some kind of interaction between the solvent and the particles. Like proteins will have some charge, that's why they dissolve in the water. So there's some interaction. So it's not going to follow ideal because there's excluded volume. And there's also this kind of interaction between the particles also. Right. So you have this potential that they could phase separate out because it's an attractive interaction. There's also repulsive excluded volume. And these things are all mitigated by the solvent particle interactions. Right. So you're going to have this thing that you expand into a viral expansion. Right. So the idea is that you're going to expand this into a viral expansion. So you have this osmotic pressure is going to be like an expansion following the viral law. So we have concentration is the first order one. So 1 over V is concentration. So it's RTC. And then you're going to add a power series. So you're going to have pi over RTC equals 1 plus B2, the second viral coefficient, times C squared plus B3 times C cubed. But you don't usually consider the higher order ones. So you're just going to have this first order, and you're going to have the second viral coefficient to describe the interactions of the colloid with each other. Right. So in a sense, like this first law will tell you that there's a pressure, right? So this pressure shows up, and that means that if you have water here, okay, right, then what's the pressure that the water wants to go through this membrane to dilute the stuff that's in here? So it wants to have the concentration the same on both sides. So the water is actually going to flow into this side to dilute the salt. So that's what happens when you go in the ocean, and your skin will swell up because of your skin shrinks because the salt water pulls the water out of your skin. Right. So it's kind of like you can see this in biology all the time. It's kind of osmosis, right? So basically, if you put tubes into this and you had a closed chamber, right, like that, and then you have the membrane, then you had your salt water, and you had fresh water here, then you'd see that the level of the water would be higher, right? And the MGH of that is the osmotic pressure. The level would actually be higher. So there's a real pressure that develops, right? So I could put a pump here, right? And I could just pump this down until it's equal, and that would force the water back over here, and then it would come back up. Or I could just put even more pressure, and I could pump even harder, and then the water would flow out. And I could pump seawater in, and I could just pump this through, right? So that's reverse osmosis. Osmosis is your skin swells up, your skin shrinks. The seawater and reverse osmosis is you pressurize your skin and pump the water out of your body into the other way, right? So anyway, here you're just pumping seawater, and then you're going to get a buildup of salt here, right? So membrane fouling is like the main issue of this reverse osmosis. So how long can your membrane survive? So what you'll do is you'll have cycles. You'll be running this thing, run, run, run. Then you'll reverse to flush the membrane and dump the brine that you made. And then you'll pump more salt water in and then stop and dump the brine, right? And then eventually something else will build up on the membrane that clogs it. Then you have to replace the membrane. So the costs are the pump, right? The flushing operation and then replacing the membrane. Those are kind of the expenses of this. And there's a pressure system that you have to set up. The pressures aren't huge, but it's enough to just get this to go, right? So anyway, reverse osmosis is one application of this. There's a lot of biological applications. This is the reverse osmosis. This is a osmotic viral expansion for osmotic pressure. So there's one homework. You already did a homework problem on this. There's a lot of kind of protein-based things going on here. So it's used in a variety of things. This is the only place in the book where they talk about it. And it just takes exactly the ideal gas, or the ideal and real gas. So here it's using the viral expansion, and it's just kind of plugging that in. It doesn't have to do with vapor liquid equilibrium, right? So it's kind of a funny place to put this, actually. This should have come earlier on. I think I mentioned it earlier on, but there is a section in the chapter about this. So that's it for chapter 11. Hopefully that's okay. Then the next thing is chapter 14. Right? So chapter 12 and 13 have to do with more, like we've already seen this. We've already seen the NRTL and these other models, right? So there's a bunch of models in chapters 12 and 13. I mean, there's probably 10 models or something. The Van Leer model is like it's just like the two-parameter Margulis, but it goes on to more parameters. Sachert-Hildebrandt uses a thing called a Dill parameter, which is also in the back of the book. So Dill parameter is based on the idea that like dissolves like. So it's something similar to this acid-base idea. So there's a Dill parameter here. It's a measure of two things that have the same Dill parameter are similar. So they should mix. That's the idea. So if you tabulate everything in terms of this Dill parameter, then you can say, can subtract the two and square it, and then get a value that tells you, do they mix or not? The other thing that's important to mixing is the density. So two things that have the same density tend to mix, right? So you can kind of consider density differences as a measure of miscibility, right? So this Sachert-Hildebrandt takes the so we had like x1 ln x1 plus x2 ln x2 plus x1 x2 times this omega 1 2 is the delta G of mixing. Right, this part's the ideal one, and this is the Hildebrandt contribution, and then this omega 1 2 has to do with some average, like an average energy of mixing, like E11 plus E22 minus E12, two of those, because it can be 1 2 or 2 1 divided by 2, then the number of coordination sites, and then divided by KT. So it's inverse temperature, because this is delta G per KT. Right. So anyway, the Sachert Hildebrandt says that this thing's going to be, this whole thing is this, but basically that thing's going to be equal to this del difference, like del 1 minus del 2 squared, because it doesn't matter which one's first. And then it's based on volume fractions instead of mole fractions. And then there's this other conversion factor here. So the original one was mole fractions and then just the del difference, this del parameter. And then this the way he's doing it in here, it's got a volume. So if you have things that are the same size, like filled circles and unfilled circles, then mole fraction makes sense, right? That kind of is going to be the thing I use here. Let's say you have things that are different size. You have, say, polymers as the chief example, right? So you have polymers that are mixing with a like with a solvent, right? So these things aren't the same size. You have a problem that if you say mole fraction, like this is a mole fraction of 50% or 0.5, right? But this is a volume fraction of 1, 2, 3, 4, 5, 6, 7, 8, 10, 10 to 1, right? So it's a volume fraction of 0.1, 0.01 for the solvent, right? So there's a big difference between considering mole fraction and volume fraction if you have polymers and solvent. The same thing for everything, really. Like you could have methanol and then benzene, right? And the two have a different volume, right? So these two don't mix, but you could say just ethane and benzene, right? Or methane and benzene. So there's a size difference between these molecules. So the mole fraction isn't exactly the right way to talk about how it fills space. Right? So the volume fraction is one of the first things they said was like things are different size. So he's got here like volume fraction introduced, right? Then the solubility parameter. Anyway, so we don't need to really understand these. We're just going to use these equations, right? So there's a variety. This is just the simplest one. They get much more complicated. The other thing is all your so these are the del parameters and the specific volumes for a bunch of things, different groups, right? And again, they're in the back flap of the book, and you can get these also in the NIST chem thing, NIST web book. So this is just that Hildebrandt one. Fleury-Huggins is more elaborate polymer thing. He modifies the beginning part of this, so the Fleury-Huggins equation is going to be, we have Fleury-Huggins theory is you had this thing. So it was a first attempt at so this is chi parameter, chi is that average energy, C over KT, right? And this is G over RT per mole. And then what Fleury said is, well, the number of moles of the mole fraction has to be reduced by the size of the chain, basically, right? So if you have two polymers mixing, the entropy is less because they're glued together. So this reflects, this is a mole fraction of monomers, and this is N is the molecular weight, the number of monomers. So the entropy part, the ideal entropy part is reduced because they're glued together, because they can't move, so they're stuck together in a chain. So that's basically that's a Fleury-Huggins equation, right? And he's modified it. Let's see, he's modified it here to make it unrecognizable. Basically, the idea of this is the same thing about the volume, right? So he's written it in terms of volume fractions, and it comes out this way. So I think he's probably right, but I can't exactly sort out how he got from this to what he has. But anyway, this is the one we're using. So basically, you need to convert from mole fraction to volume fraction. So you have volume fraction is the mole fraction times the density. Let's see, times the molar density, or 1 over the molar density. So the molar density is the specific volume. So it's X times the volume. It's X1 times the volume of 1 divided by X1 volume of 1 plus X2 volume of 2. So if you have the molar volumes, which are tabulated just previously, right, somewhere. So we have molar volumes here. And then you can just, to get this phi, which is volume fraction, you go through like X times V1 plus X1 times V1 plus X2 times V2. And then you can get those parameters to put into this Flory-Huggins. And then you use the volume fraction. So a bunch of the equation state use volume instead of moles. So there's a bunch of them have this volume fraction to calculate. The del's tabulated. So the question is, like, you're going to get these mega equations like this. So this is the Mosed S-SED theories, models, right? So it's just going to have more and more parameters, right? And you just have to, so you don't need to understand what's going on here at all, because you'll spend a lot of time. So this Paul is the thing you have to calculate. You get it from tabulated values of these Q's and taus, right? Which are like dispersion is lambda, polarity is tau. You can see they're related back to things, molecular features, but an AB is the acid base parameters, which here are temperature dependent in this model. So it's inverse T, right? Basically, this is going to get, these are empirical at some point. It's just a bunch of parameters, right? And then it works. So basically you use it because it works. The parameters have some kind of an argument for why they exist, but you don't really need to consider that when you're using it, right? And you might want to, if you want to develop a new one or figure out what went wrong, basically you're just trying to use these things. So from our point of view, we're just using these. You can see like lambda and tau are just tabulated for different chemicals. So this is all part of the kind of group contribution idea. So you're going to break apart molecules into groups, and then you're going to have these parameters that have to do with the groups. So whatever model that you're using, just look it up in 12 and 13, get the basic equations, and then do the calculations. That's the idea. You don't need to understand them. You just need to use them. So just try to minimize your understanding. Okay. These universal quasi-chemical, so uniquac and unifac are two universal quasi whatever, right? So they're based on directly on group contribution. So these will have a table of type of chemical groups. You break up your molecule into the chemical groups in it, and then you pick the numbers that have to do with that chemical group and the number of those chemical groups. And then you use a formula that's going to take those numbers that you got, the R and capital Q, and then generate these other parameters that you stuff in to get the activity coefficient. Right, so this is all programmed in Excel. He's already got it in Excel. This is all programmed in Aspen and in ChemCAD. Right, so these things are already all programmed for you. You just have to like these activity coefficient files. So like 14.3 activity coefficient files. So you can see it's got all the models at the bottom. See if that will expand for me. I asked it to. So it's got NRTL. That's one from that paper. So NRTL and NRTL5. It's got Margulis, which we've already dealt with. It's got Unifac, Uniquac. It's got all the models in it. So each one is going to have, you say, all right, if this will ever open. I guess I'm not going to wait for it. But basically, oh, maybe it didn't get that I wanted it bigger. No, it's just not getting anything. There. All right, so if I go to, see, I don't really want to leave where I am. Let's see, which one is it actually in here? It's in LLE, okay, that's good. So if I go to like Unifac, right? So it's vapor, liquid, 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 but it'll ask me which chemical groups do I have? Okay, so like here's the subgroups and the numbers, right? You put in, oh, this is just the Unifac table of the values, right? And if I do like Unifac, that's the AIJ numbers. And then this is Unifac VLE. This will have you put in those numbers. So here's the table. You put in how many methyl groups are in isopropyl alcohol is 2. How many methylene groups is 1. How many hydroxyls 1 to make an IPA. And water has 1 water, right? And PA, I don't know what that is, but methyl ether ketone. So those each chemical is going to have a signature number, like code here. and the code's going to pick from that table to generate the gammas. And that's all programmed for you. You don't have to do it. But it's going to calculate, these are the Anton coefficients, and then it's going to spit out a gamma here somewhere. So the program, I'll show you how to do this after. But basically, it'll spit out a gamma for that. Right? This guy's actually should be on LLE. So that's kind of what way these UNIFAC things work, right? And then what else? UNIFAC has the tables. I mean, it's got to do with the molecular volume, surface area, activity coefficient, both, or activity coefficient, what you're calculating, surface fraction, blah, 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 right? So there's different features. So there's a variety of these models, right? So those are kind of the ones we're going to use, like UNIFAC, UNIQUAC, NRTL, Florey-Huggins, and then so there's a few we'll use, and it'll give you a feeling for kind of using other models. So every field that you're in is going to use a different model, like petrochemical, UNIFAC, biology, like NRTL, whatever. So each one will have a separate polymers, Florey-Huggins. So basically any field you get into, it's going to have its own activity coefficient calculation method. Right? And you just have to just sort out, be able to be flexible enough to find the parameters you need and just plug and play. Like you're not trying to really totally understand unless you really get involved in a certain field. But for our purposes right now, we're just using these things, because trying to understand all of these is going to take, it would be a whole course. It'd be like a graduate course, even it wouldn't be an undergrad course. So there's no point in trying to do that. What we're trying to do now is just understand how you do liquid-liquid separation. Like in the last problem, we're trying to do liquid extraction, right? So you have biological with water and some organic in it. You want to remove it, so you put an alcohol to pull it out. So you do liquid-liquid extraction. Then sometimes if you do steam distillation, you mix a liquid with another liquid and then get a vapor equilibrium. And you shift the vapor equilibrium by having the water in there. So that's liquid-liquid vapor. And then if you're looking at crystallizing out a solution or dissolving crystals, then you have to look at solid liquid equilibria. Right? So we've done vapor liquid, and then there's all these others. Right? And a lot of times these are the most important thing. Like even in the last problem, they used liquid-liquid extraction. So it's liquid-liquid equilibria. And then they went to liquid vapor phase behavior for binary mixture to distill it. Right? So you have multiple steps of separation. You have to have the liquid-liquid and solid liquid are important to that. So so I'll talk about that next time. So I'll quit here and I'll do the next day, which would be Tuesday. Okay. Email me if you have questions.